想问一下，就是对这个引力的弱场近似，就是说现在是在做这个超辐射的这个半径嘛，它现在是这么一个问题，找一下这个图。
让云龙欠一下。
就是它这个是个半径，然后这个是超辐射的这个黑洞，然后现在它要做的是从这个黑洞周围，在有了半径之后，这个不规的变化。然后它这里是给了一个，就这个表达式。
要不明天吧，明天上午吧，这会儿有份报告了，好吧？
哦，
对，
对。
I'll see you on Friday. Oh, when did you come? Last Thursday. It's like you're got here. We met in passport number, and everything. Sure. Oh, yes. Thank you very much. 外援都长成这个样子。因为图上是这样的。
基本怎么这么晚才能考？不是，这属于那是你签过的，属于他们的一个部分。
我在哪签？这两个地方，
对，
现在
不，一是
一水不足，都确认了，就是所有委员行吗？还是我们都行？我要一水不足，签来的。
因为上次是签的，一是不足，
三个都可以。
哦，你也三个，
对，看起来不是，护照。
上个写的是上个是一个。这个属于他们学校的任务。
Mostly conventional. No.还是看的文章好像是我想的好。So already 是今年，今年是this way。我今年。I mean the person who. Yeah. What is the name? Close to here. 今年。So about the Asian ICT. Okay, ICT. 今年 is ICT. It's quite close to here. Another one. That's the same way as KIT. I think so. KIT. Yeah, it's the different cloud. I see. So he's not using these pictures. All right. Yeah, this is the KIT. Okay, but later.
Later does not work because this screen is special.
I see.
Okay, so time is up. So let's move to the second talk of this seminar. And in this second talk, we are very happy to invite Professor Keun-Young from the Gwangju Institute of Science and Technology. So he obtained his PhD in 2009 at the Stony Brook of New York University, and then he conducted 2 postdoctorate successively at the Southampton University in UK and Amsterdam University in New Zealand. And then he is now a professor at the Gwangju Institute of Science and Technology at Korea. So he will give us a talk about machine learning approach to holography towards holographic strange methods. So let's welcome. Yes.
Thank you very much for the very detailed introduction. So actually, I was just wanting to visit Professor Lee, but he kindly he gave me an opportunity to talk. So today I'm going to talk about these machine learning things. Maybe one of the reasons I just chose this topic is that I want to get some feedback from the people here. I would like to be very slow, and I'm not going to try to explain the technical aspect of the machine learning. So it's another story. My point is how to use this machine learning technique to study physics. Okay, so before starting, this is my campus. And it's here, the Gwangju is here, Seoul is here, and maybe Beijing is somewhere here, right? So it's not that far, just a 2 hours flight. From here to here, it's the close in terms of time. It take more time. Okay, so I guess many people are familiar with just the basic concept of the holography. In essence, it says there's some gravitational physics. This represents a black hole, and you can imagine the screen here. And the quantum field theory or quantum system lives on this boundary. And for example, this quantum system can be quark-gluon plasma or a high-density superconductor. And this is black hole. And you can see this white one or green one is kind of effect of this space-time or black hole. And the effect will determine the property of the quantum physics at the boundary. And so regarding the machine learning, we can ask 2 questions here. Here is a quantum system, and there's a space here. We call this a bulk space-time. And one question is, can we understand this extra dimension? This is the field theory direction. There is extra dimension. Can we understand this extra dimension as a deep neural network? It's a quite interesting question. Or regardless of that question, can we use a deep neural network as a useful tool for holography? It's just a technology. We have 2 questions, and I would say the answer is positive for both. Today, I'm not going to talk about the first question, but I'm going to focus on the second question. Okay, so the schematic understanding of the deep learning is just technique. Traditionally, we study applied holography can be studied in this way. We start with some gravitational model. And this is basically model building as a speed of the bottom of holography and make a prediction. And that prediction should be compared with experimental data. Is it okay? Oh, I see. Ah. Okay, well, let me continue and make a prediction. And if this theoretical prediction does not match with the experimental data, then you go up and you change your model, okay? And you do again until you get the agreement between the prediction and the experimental data. That's a traditional way of research. And if we use the machine learning, then instead of doing that, we start with the experimental data. It's a big data, and machine will tell you about the gravitational model. And by using this model, you can make another prediction and try to make another experimental data to match the experimental data. So then this way of research, I would call this an AI method. Okay, so this traditional method, in order to study this, we need intuition or some principle to make a good model here. So we need sometimes genius to think about a very, very good model. However, this AI method, we don't need a genius. We need a machine, good machine. The machine will give us a model, and we just use that model to understand the physics. And if it works, then we try to understand what happens. Okay, so I think this is an important thing. So sometimes people say machine learning answer does not, say anything about the physics. I think I would agree, but we are human beings. So after knowing the answer, we try to understand the principle. And if we can understand the principle, I think that's why we use the machine learning. So not just knowing the answer is not enough. But as you know, sometimes there's a very difficult mathematical problem. But once you know the answer, sometimes you right away understand what's happening, right? But the knowing answer may be difficult. So then for that, we may use the machine learning. That's my point. So normally when we study the science, so we are very familiar with these model building things, or sometimes we use the very big supercomputers. And now, in a supercomputer, we also can use the machine learning type understanding. And this machine learning now are used also the string theory. And this is the review paper for the string theory. And here is deep learning, ADS-CFT, and holography says something about my talk here. And also this is another review paper. Here there's a theoretical particle physics. It's also using machine learning technique. Okay, that was a general introduction. And for a specific purpose, I'm going to introduce this paper. This paper is by Professor Koji Hashimoto in Kyoto University. I learned the original idea from this paper. And when I read this paper, I realized the basic idea also can be used for general problem, not only holography. So I just made a simple paper. The title is ADS Deep Learning Made Easy, a simple example. What I did here is the machine learning technique here, I just used to solve the classical mechanics. The main purpose is twofold. First, I want to deliver the main idea by using the simple example. Then people who does not know about anything about holography can understand what's going on. The second, more important purpose is I need a train. I need to train myself to solve the problem. So I just chose this problem. Problem is very simple. This is one-dimensional motion. You may imagine there is a gravitational force. And then there may be some mysterious force depending on this position. But we don't know what it is. Then we have to solve Newton's equation to understand the trajectory or the final velocity of this motion. Then this is basically F equals ma. This is ma is F. And this force has a gravitational force and this mysterious force. Okay. Normally, what we are doing is if we know F, then everything is very simple. We can just solve that. But suppose this F is very complicated and we don't know what it is. Then traditional way is we use some intuition. For example, somebody can say, okay, F is if it's a friction force, then maybe it's proportional to speed or proportional to speed squared, or. But I just chose this is put F is a function of X. It's a little bit mysterious force. But suppose there is some force. then we don't have any principle. You cannot guess anything. Then mathematically, probably you will try some polynomial form. For example, ax plus bx squared plus cx cubed, something like that. And you just compute numerically and try to compare with here, my big data is initial position and initial speed. You have many data sets here. And at the final position, you have a speed. That's your big data. And we have to find out force matching these big data. Okay. Then again, let's go back to the principle. So you will maybe you may want to assume polynomial form ax plus bx squared plus cx cubed. Then now you change a, b, c and try to match the final all big data. Okay, that's the normal traditional way. Sometimes it works, but if it does not work, then probably you want to add more terms forever. But this is not so clever way, but that's one way. Now, my point is, instead of doing that, just we can hire the machine, and then we can just ask machine to do that instead of by ourselves. Okay, so this is the simple result. This gray one is the true force fx. I just made it. So, and then machine start with this red one. This is random. Machine start with a random force, and then machine just try to repeat by changing the force form, and at the end of the day, after 500 trials, machine just found the correct form. This is green. How machine finds it? Just doing this. We know the experimental data VF. For example, we have 100 of the experimental data, and the machine just guess any force. Then of course the final VF will not match to the experimental value. Then you just think of the difference, right? Experimental one or the trial one, and you just add the all difference. That's called the loss function. Then try to remove loss function to vanish. Okay? You try to vanish loss function by changing this f. And at the end, machine succeeded to reproduce the correct f. Okay? So I don't explain how machine do that, but let's accept we have a very good machine and just ask machine to do that. Does it make sense? Okay. This is basically what causes it for the holography. So, this is not the code's original way. This is another way, but I just explained the basic. Let me just summarize the basic understanding here. You have a big data. Big data is you have a many experimental data, initial speed and position, and final speed, right? And then you use that and you try to solve numerically this ordinary differential equation. And the machine, this is machine part. This is a deep neural network. I'm going to explain this later, but the main role of this part is machine assume f, just randomly, right? And just solve this equation. And here, this is experimental result, the large V, and V is the machine's result. Because f was random, of course, this is not zero, should be different. So some number, let's say 1 or 2. But you have a 100 experimental data, it may be 100, something like that. And you want to make this 0. That means your the machine's answer should match to the experimental result. Until then at the end, if this is 0, that means f is correct. Okay, that's the basic idea. Okay. Another interesting problem is this integral problem. So this is a disk. And imagine there is a charge distribution on the disk. There is a radial symmetry. So that's why this charge distribution is only function of R. And you can measure experimentally the electric field strength on this G axis. Okay. Then in the general physics textbook, you can find out this the formula. So this is sigma. If the sigma R is given by integral, by this integration, you will get the electric field on this Z axis. Okay. So you can immediately see once sigma is known, just integral is easy. Now you can imagine the opposite situation. You don't know sigma, but you can measure electric field experimentally on this z-axis. This is given, then the question is what is sigma? That's the question. So this plays a role of the big data because this electric field strength should match with every position, every z position. Then we have a big data here. And the same story, this is the machine's result. The machine, actually, this curve is the assumed charge. This is a real, true value. But the machine will start with some random distribution like this one. And you put this one here, then of course EG does not match with the experimental value. Then the difference is a loss function. And the machine now try another one. Okay, this one, and do that again. Try another one, do that again until this becomes 0. And this becomes 0, that means now machine just trained the correct charge distribution. Okay.
Yeah, I think in this setup, the solution is not unique.
Very good.
Right. There are many different.
Very good. That's a very good point. There's a possibility of the multi-solution, of course. That's a good point.
You can cook many sigma.
Sure. Yeah. There's a possibility of multi-solution. In order to avoid the multi-solution, I would say this should be complicated enough. Then it's okay, but this is too simple. So there's a possibility. Yeah, I agree.
And in this practice, how many layers?
In this case, we just chose 3 layers.
3 layers.
And then maybe 3 or 5 nodes, very simple one.
I see.
Yeah, very good. Okay. Good. So I'm going to come back to that point later, but here, my point is I want to deliver the main idea. Yes. So I just explained 2 examples. How to solve ODE and the integration. But you know, the physics is full of differentiation and integration. Then this technique can be applied to many physics problems if you are interested in the inverse problem. Okay, so let me try to generalize. So what's happening is the first example is this f is unknown. So the point is everything is known, then numerically solving differential equation is straightforward. Then suppose you don't know f, then you are using the big data as a boundary value or initial value. Then you have to guess, or machine have to guess what will be the answer. Let's generalize. This is one specific example of this general form. Then this red one can be unknown. Now your problem is you have to solve this equation, but A, B, C, F is unknown. You don't know that. Then how to solve that? Of course, you cannot solve. Then you are given lots of big data as an initial value or boundary value. Then what machine is doing is this. Machine try A, B, C, F randomly and try to match all boundary data. If it does not match, that means loss function. And here loss function is the machine's result minus real result. So that's the loss function. If loss function vanished, that means you found the correct A, B, C, F. Okay, that's what machine is doing. Let me generalize once more. There is only one function f and only one variable z. Then here I have a coupled equation. I have 2 functions f and z, and now I have unknown a, b, c, d, e, f, g, h. But you know, the complicated problem, but the basic principle is the same, right? The machine is trying to find out these red ones by using the boundary data. Now, so the reason I generalize it this way is to explain this equation. So you don't need to understand what this equation means, but the mathematical structure shows there are 2 functions, ax and phi, and they are function of z. So it's in this form, right? And here this f is unknown. It corresponds to the in-breaking factor of the background of matrix in the context of the holography. so now this AX is basically gauge field in the holography, and this phi is some scalar field, and this AX has something to do with the conductivity. And in holography, the conductivity will be computed by the boundary value in the holographic direction. So now you have an experimental value at the boundary, and you have a parameter, then you have a big data at the boundary. And in order to match that boundary data, you have to choose the correct F. Okay? That's the whole structure of this method. Okay? So my point is, if you can solve this problem, of course you can solve the others. Okay? That's the idea. So about this integral problem, let me generalize. So this can be understood like this. And there is some functional. The functional has two functions, f1, f2. In this case, f1 can be sigma, but no f2. But in principle, you have more functions. And this is the integral over r, that's the holographic direction. And you have some parameter, alpha. You need this parameter because you need the big data. So every alpha will give every value. So that plays a role of big data. And we can generalize once more. This f1 and f2 can be the g can be a functional of the other functional. And you have these coupled integral equations. Okay, and this a alpha and b alpha, you have big data, and you want to find out small f1 and f2 in the integral. Okay, so the reason I generalize in this way is to show this equation. Again, so let's just focus on the mathematical structure. Here, this L is function of D star. D star plays a role in alpha. This is a specific point at the holographic direction. And Z, this is a holographic direction. And this formula, this two coupled integral, is necessary to compute the entanglement entropy. So when you want to compute the entanglement entropy in a holographic way, you need to do these two integration. Okay? So this belongs to this problem. Okay? Then we know entanglement entropy at the boundary, then we can ask what is the bulk field, for example, in breaking factor, giving this boundary data. Okay, so it's a summary of the idea. So normally, yeah, there are many complicated or deep idea of the physics or mathematics in the field, but you have experience. At the end, it boils down to some differential equation or integral equation. The holography is the same. Actually, we have to understand many things to really understand the holography, but the computational sense, it just boils down to the equations, differential equations, integral equations. And the whole point is, in a traditional way, A, B, C, D, the red one is already known, and you just straightforwardly solve. But now, our question is inverse. It's inverse problem. A, B, C, this red one is not known, but we only know the boundary value. Then, in order to match the all boundary value, what the bulk field should be used? That's the question. And we can use the machine learning to get the bulk fields. Okay? So this is classified as an inverse problem. And in some sense, it's optimization problem because our loss function should go to 0. Okay. Good. So that's I think I finished the basic scheme. Now let's go to the problem I really want to solve. Maybe this part I need your feedback. So here, in terms of ADS-CMT, this QPRED or non-Fermi liquid is the most popular subject. And I think it's because there's a universal property of this non-Fermi liquid. Here, universal means the microscopic structure or constituents may be very different depending on the methods, but somehow some property is universal. So, for example, the DC resistivity, the linear T resistivity property means as temperature, in terms of temperature, this resistivity is linear for many different materials, in particular for the strongly correlated electron systems. And there's another one, it's called the Hall angle. It's also measured at the finite magnetic field. In the finite magnetic field, you have two kinds of conductivity, and the ratio of these two kind of transversal part and longitudinal part, the ratio is proportional to t squared. So it's arguable. This is really the universal property of the strange method. Of course, it's arguable, but I think as a zero-order approximation, as a theorist, this is a very attractive property to understand. So there was a review paper in Science. The title is very interesting, stranger than matters. And here there's a table explaining the current status of the universal properties. And here there is a linear theory. There are two things: high temperature and low temperature case. This is a whole angle property. Of course, in some materials, the whole angle was not observed. So maybe already here people can claim, okay, you don't need to worry about this. This is not universal. You can claim that. But again, as a theorist, it's as a zero thought, I think it's enough universal enough, right? So then this is experimental the summary. If we go to the theory, then there is a traditional the CMT theory explaining t goes to 0. And also interestingly here, it's SYK model, is a CF, EMD model says also explained in some way this linear theory distribution. However, interestingly, there's a missing part here. Here there is a whole angle t squared, but here there's no whole angle t squared. I don't know why, but maybe there's not many things to highlight in terms of theory. So I may be wrong, but in the holographic model, there's no, consensus about the t linear distributive plus t squared whole angle together model. But there are some models explaining this one, or there are some models explaining this one, but there is no consensus on the explaining both at the same time.
Yeah, in the proper brand limit. Yeah, we can do.
Yeah.
But in the fallback direction,
Yeah.
I don't know.
Yes, yes. So it's very simple problem to ask, but very hard to answer, right?
Yes.
This is the machine can do. This is the problem machine can do. Maybe the human beings are lack of imagination. Yeah, sometimes if we know the answer, then we can understand. So that's my basic motivation to understand this ADS-CMT by using machine learning. So this is our favorite model. Actually, many people, Lee also a worldwide expert on this model. So this is called Einstein-Maxwell-Dilaton model, very simple model. So we have Einstein terms, scalar terms, and Maxwell terms. And here, this is called axion, but it is introduced to for the momentum relaxation. So here there are three unknowns, Z, V, Y. Okay. So when this model was introduced for the ADS-CMT, what people did for the first time is very, very traditional way of science. Okay. Normally, theorist does not like numerical work and wants to do some symmetry or some the universal property using the IR dynamics, something like that. So people just assumed Z is this exponential form, V is this exponential form, Y is this exponential form. And this is very clever because by assuming this, the metric is solved in this way. Here we have three parameters, gamma, delta, lambda. Here we have three, theta, z, zeta. They are related, the three parameters, but we have a very nice metric form here. By using this very nice form, we can understand why the distribution can be linear or not by using this. Okay, this is very good, but no t squared yet. Maybe I think the conclusion is there's no case, right? Maybe that's the conclusion in this setup.
Yes, I agree with you.
Right.
With Elias and Sarah, we can do the proper limit. In that setup, you can find some regime.
Yeah.
And both linear and particular behavior. But as you said, with fallback direction, no model.
Right.
No model.
Then probably the next step is we have to add more terms. Then maybe this will be more complicated. Sometimes it's not analytic. But anyway, that's one of the theoretical possibility. You can modify by adding something here. Okay. So I just made some sequence here. For example, this, let's say this blue one is the capacity of this model, original model. But this green circle means we just assume Z, B, Y has this form. That's the green circle. But we have still room here. We don't need to assume this. It has more potential to explain something. And with this, you can add more terms. You have some variance. That's this red one. You just modify this model by adding more terms. And another possibility is just forget about this. There may be better model. That's, I think, it's in the purple case. So we have many, many possibilities. What I want to do is very humble. Let's not try some dramatic things, but let's try to understand this model better. Maybe this part. People already, I mean, the many analytic work, it's already exhausted. I mean, green part is fully understood. And this part, I think it's not analytically approachable, but still numerically we can explore. But this is too wide area to explore numerically. You have an infinitely many way of choosing Z, V, Y, right? So my point is we can use machine. We are busy, but we can use machine. The machine can explore this area. And that's the point. Right. Good. So then that was my middle ultimate goal. And in order to do that, let me just introduce what I did as an exercise. The exercise is two exercises. One is a deep learning bulk space size from boundary optical conductivity. Here, the big data is optical conductivity. This omega is the frequency. So because omega is a continuous variable, we already have a big data. Okay. So for a given optical conductivity, we can ask what the space-time metric should be. So this, for example, is a red one corresponding to this red, and here this blue one corresponding. This is in Blackman vector by using the different chemical potentials. This is just exercise. We didn't use something new. We didn't learn something new because everything's already known. This is a very simple model. Everything's very easy. But you know, this is again standard. I mean, strategy to learn something new. So this new numerical strategy, machine learning strategy, should be able to reproduce already known result. So this is kind of exercise. Another exercise I did is the entanglement entropy. Entanglement entropy means basically, so here there's a one-dimensional line, and we can define entanglement entropy for different L, because L is a continuous variable, so you have a big data. And entanglement entropy at the boundary has something to do with the extremal surface area here. And as I said before, it has something to do with the integral. So here, this is the entanglement entropy data at the boundary in terms of L. And we can ask what is the metric here. The metric, we have two components, the G and H. And G and H, so you can see the machine learning found correct G and H. It's already known by using this big data. Okay. So this is two exercises.
But in the first plot, the blue one, we see the clear deviation on the right side.
Yes.
Yeah. What?
Right. Yeah, we tried to minimize this, but we failed. But it was okay for us because it's exercise.
Yeah, your H is good, but the G is
yes.
not good. Yeah.
Yes. I agree.
Yeah. I see.
Right. Now this is the real one. After doing two exercises, okay. So in order to actually, our ultimate goal is to find to check if the EMD model can find some potentials for linear T and the whole angle T squared. But it's a too difficult problem. So let's first focus on the linear T problem. And of course, experts will say, okay, this is already solved. We know analytically what happens. That's true. But again, we can ask this question. Suppose we don't know the analytic solution. Then machine really can find it without any knowledge about analytic form? I think that's again the effective question. If machine learning is really good methodology, then it should be able to reproduce some results, analytic result, without help of the analytic result, right? So that's one thing I want to say. So it's the same thing. Okay. So in order to do that, let me explain another method. I'll be back here again because this is technical. Okay, I'll be back here again. Let me show the result first. So this is an EMD model, and this model is called the Gupsa-Loka model. The reason I'm showing this Gupsa-Loka model is Gupsa-Loka model is the one very standard model explaining linear T resistivity in the EMD model setup. And the question is, okay, let's suppose we don't know this, and the machine can really find this model by himself, by itself. That's my question. So in order to check that, this is the test big data. So actually we didn't use this one. We just used this part, right? So red is linear, orange is linear. Do not look at this. Everything is linear. Then the question is, machine can find out the corresponding potential V and Z. That's the question. Actually, there are three things: Z, V, 1. But we set Y equals 1 for simplicity, because our purpose now here is to check machine really can find out Gupsa-Loka or not. In the Gupsa-Loka case, Y is 1. So in order to test, we just said Y equals 1. And we didn't say anything about this. And we just gave this linear resistivity. And the machine's answer is this. Depending on this color, the color difference is everything's linear, but the slope is different, right? Only one slope matches this Gupsa-Loka. The other slope is different from the Gupsa-Loka's case. Then by using this, this is the machine's result. The potential V is almost same. Of course, a little bit difference, but there's no big difference. But there is a difference here, Z. And you can see here, this yellow one is Gupsa-Loka case. It's a very smooth, linear, and goes to the saturated values. And that corresponds to this value. That corresponds to this value. So machine precisely found this potential with some error. So then I cannot say precisely, this is numerical one, but the reasonably precisely exponential value, and this reasonably the value, right? So then the first conclusion is machine is able to find out Gupsa-Loka. That's the first lesson we learned. And I still pretend we don't know anything about this analytic method. But one thing I can learn from this machine learning is this linear behavior has something to do with largified behavior here. And this the common thing of this largified behavior is it's always 1 over square root 3/5 here. But the multiplication factor is different. If this is 1, that's Gupsa-Loka. But if it is not 1, then it's something different. But the whole point is, if you have some potential at the largify this exponential behavior, that will give you the linear resistivity at low temperature. That's what machine is telling us. Okay. And here you have this bump, steep behavior. That is reflected here. You can also see the bump, and this dip. So this part has something to do with this. And this flat part means Z5 goes to 1. This is the ADS condition at the boundary, a simple ADS condition. So somehow we can qualitatively understand, okay, in this framework, what's important? what's important is Z, not V. And the Z behavior here has something to do with here. And this linear one is related to the exponential behavior, something like that. So we learn from the machine.
One more question. So in your scenario, when you consider the machine learning, so do you consider any constraint on the capital Z, so that in the UV, Z goes to 1? Do you consider this constraint?
Very good. Yes, yes, we impose already.
I see.
Very good. That's a very good point. Here, in principle, mathematically, we can just set everything free. However, we have a physical constraint, and the solution should be asymptotically AES. Then we have to impose that. So this part is not machine found. This is our constraint to be imposed already.
I see.
Yeah.
I see. I see. Good. Thank you.
So just an exercise. So we try to use this one. This one is a little bit different. It's a linear, but we have a finite intersection, a finite residual resistivity. So by using this data, we wanted to check what's happening for the Z potential part. So as you can expect, here the characteristic thing is the exponential behavior. But here, if you have this residual part, the exponential behavior just disappeared. And it's saturated, the potential saturates some value, and that value has something to do with this value. Okay, something like that. So again, there is some cursor here, and then there's something to do with this. Okay, so this is very preliminary. So I don't claim I learned something very interesting here. No new physics here. But we have a clue what we can do. So my point is here. First conclusion is machine can really find out the groups of local numerically. That's number one. And then number two, just by looking at this potential term or by changing this potential term, we can see the change in the resistivity data. So then if we really want to have a linear T and T squared whole angle, then we can see what's changing here. Okay, so then we can learn something. Then, for example, suppose the correct answer is this one. Suppose, of course, this is another answer. Then we can immediately ask, okay, something happens here, and this has a physics. Then we have to understand what's the physics behind this. But without this numerical result, everything is perfectly okay. So we don't see which part we see. But now, if this is the case, then we see, okay, we have to look at this part. That's what I want to get from the machine learning. Okay. Good. So maybe I
have enough time. Don't worry about time.
Okay. So then this is everything I want to tell you about the big, story. Why I want to use the machine learning and in what sense I'm using machine learning. So then the last one, I can explain a little bit about the machine learning itself, if you are interested in.
Yeah.
May I continue?
Yeah, yes.
Yeah, you can stop me anytime. Okay, so now let's talk about the machine learning technique. So, okay, so this is the very basic building block about the deep neural network. So this is not deep neural network, this is the one neuron. So the idea is very simple. In the neuron case, you have some inputs. In case you have 3 inputs, and you will have some outputs. Okay, so from input you have to decide what output is. Then here the idea is very simple. Sometimes the x1 can be weighted by w1. So sometimes you have to determine this is important, this is not important, something like that. That it will be you can assign some numbers and you can weight the importance of these 3 guys. Then this is w1 x1, w2 x2, w3 x3. This whole number you got now. Now you have to decide this number is really big or small. Then you need a reference, right? This is your reference. For convenience, you can think about this as a minus b, just for convenience. Then you said, maybe I have an example here. Okay. So 0.1, 0.1, somehow this is your input. And W, 1, 2, 3, just I made 1, 2, 3. Then after computing this, you have a 0.7. Then you have to decide if this 0.7 is really big or not. You need a reference, right? Then if in this case, for example, you have a 0.7, and if you add, for example, how can I say? Yeah, sorry. Let me do again. 0.1 times 1, 0.2, then this is 0.6. Then if your B is 0.1, then final answer is 0.7. And if your the B, wait, this is called the bias. How biased you are. Then if it's 0.5, then it becomes 1.1. Then you have to determine this is big or small. And then this sigma is called the activation function. For example, if I use this activation function, then if this argument is 0.7, it's 0. If it's 1.1, it's 1. So you turn on or turn off. Okay. So when you decide that, this bias also important. Okay, that's what happens. It's 3 numbers, weight, give bias, and decide on and off. Okay, that's how you information is transferred. Of course, this activation function, this is very conceptually easy to understand, but you can use different, more smooth activation functions. But this is very technical part. I think this is called a rectified linear unit. I mean, this is a very popular one people are using for deep neural network for the technical reason. But anyway, this is basic idea. Now you can connect. This is just one thing. Then you can connect in this way. Then, for example, this is your one input. Then you have the 2 weight, right? And then here you weight and bias will determine. You will give some numbers here. Then number will weighted and biased. Then and the output number will be weighted and biased. And finally, you will have some number here. So you give some number, and after doing this network, you have another number. This is a function. So here z, you can imagine the function z0 from 0 to 1. Every number of z, of course, discrete number, will give some number. That's a function, right? So that's how deep neural network is used. You can just construct arbitrary function by using this deep neural network. What function is decided by these W and B's. Okay. Good. So then let's have some exercise here. So this is the data, this curved data. Now we want to make a function, fz, feeding function for this data. Okay. Then so if I make this, so this is basically, you can simply imagine I have 2 numbers and this corresponds to this, and that's a bias factor, and this tangent hyperbole is my activation function. And you have this number, and the number will be weighted by this 2 by 2 matrix here, and add bias, and again activation function, and weighted by 2, like that. So then this box is all parameters you can change, right? Good. Then, so this is the final result. So actually, I prepared the animation, but this became PDF file, so I cannot show that. So what's happening is you start with this red line, and machine is changing this line, and at the end, it just fit this. In order to have this curve, these boxes must be this number. Right? With this number, you just give one z, then it gives you correct fc. So this is strange looking numbers. Sometimes people say, okay, because of this, there's no physical meaning for this neural network, because just a random number looks like random. I agree with that. In this case, it's just a random number. Right? And then, so, okay, in this case, it's a 19 parameters. The number of boxes are 19 parameters. You have to change it 19 numbers to fit this curve. in order to visualize, you can think about this curve this is the surface in 3 dimensions, but actually this is the surface in the 20 dimensions, right? This is the 19-dimensional space, and you have 1 dimension here. So then the point is, every point in this 20-dimensional space, you choose one, that means you choose different number, then your loss function will not be 0. And you start from here, for example, and the machine try to find out here, because the loss function should be 0. Then this is now a mathematical question. You have a surface, very complicated surface in 20 dimensions, and you start with some arbitrary point. How you find out the global minimum, which is 0? Now this is a very complicated problem. Don't worry about that. That's not our job. We can borrow some package from the machine learning guys, okay? So we just borrow. Then the basic idea is just to follow the steepest descent way. That's just one way, but that's not that simple. So the machine learning guys developed many methods how to find out the global minimum. And as Lee asked correctly, we don't know if there is a really one global minimum or many global minimums, or sometimes it just go to the local minimum, it does not go out. Yeah, you can easily think, so you just follow steepest descent way, you just go to track in the local minimum, you never go out. But you don't know you are in the local or not, right? So then machine learning guys already know that they are not stupid, and they developed many methods how to escape from the local minimum. Okay, so that's the thing. And there's another general question we can ask is this a unique design? So Lee asked about how layers. So this is number of layers, 3 layers and 2 nodes. However, I can also do this.
Yes.
And then, of course, by using that, I have 71 parameters, much more complicated. And this strange looking number is the correct numbers for this design. So there is a very interesting mathematical theorem. That is the universal approximation theorem. That means you can always find the deep neural network design to fit any arbitrary curve. So you just give any arbitrary curve fz. It can be very complicated, but you can always find the machine learning deep neural network reproducing that guy. That's the universal approximation theorem. But you feel something strange because you can imagine many complicated curves. It's very complicated curve. Then if I use, then probably you think maybe I cannot reproduce that complicated code just using the simple one. Sure, that's true. This is the existence theorem. Then the answer is you have to use more complicated one. Then if you are using correct one, then you can always find out any curve. Okay. So then that means again you need some experience. Sometimes this design is wrong, then you cannot find the correct answer. But you can say this way, okay, then maybe we can use a very complicated design from the beginning. Of course, then that will be okay. But if in that case, you will spend lots of computing time because these parameter numbers will increase much more. So you have to find an optimized design.
I see. So my question is, regarding your theory, so it's an NP problem or is solvable with a P problem?
That I don't know. So I don't understand the terminology NP and P.
In some sense, so maybe the system is very complicated, and then you have infinite number of parameters. So in practice, it's not durable. Yeah, in principle you can, but in practice you cannot.
Right. I don't know the answer right now, but in this case, what I want to say is just finding out the correct design itself we don't have a general, nice principle. It's just a trial and error.
Yeah, because we know in classical mechanism, we know when we're waiting for a long time, every particle will recover to the inertial point.
Yes.
Yeah, but the time is
Yes.
unacceptable. Yeah.
Right.
Like you see the story, if you have very complex system, maybe we cannot handle. Yeah.
Maybe.
Although we have a principle to say.
That's right. I agree. Yes.
I see.
Okay, so that's the basic idea of the by the way, any more questions about this deep neural network technique? So if you are not if you don't have any experience on this, it looks very scary, but you don't need to worry about that. I mean, even undergraduate students can do this after 1 week. If you understand the Python. That's a preliminary knowledge. Okay.
So Mathematica have also a tool for this.
Sure. So actually, I used the Mathematica for this one, but I wouldn't recommend if you just do the research problem. This is too slow.
I see.
Time is important. But this simple problem, of course, Mathematica can do that.
Okay.
Okay. So I'm going to go very fast. So this is the holographic computations for the. Okay, let's just skip that. It's not very important. Yeah, so let me just skip. Good. So maybe let me summarize with the outlook of the. Yeah. Okay, so now what we are doing is we are doing some two things. We first need to understand and develop the methodology. So how to use the machine learning for ODE, so this is very interesting idea, PINN. Maybe I can explain that later if you want. Maybe I like this name, physics informed. So we need a physics. It's not just a black box. And how to, I just focused on ODE, but PD part is also important. And we can use another physical quantities to understand to use the machine learning, like Alpers data, fermionic spectral function, and more quantum information theoretic properties like complexity. But anyway, so my ultimate goal is to try to understand this linear T and T squared model. And regarding that, I'm now here. So in summary, I would like to explore this blue region by using the machine learning. It's not guaranteed, but maybe I don't know. But there may be some model here, but there may not. Then I have to extend the red, and maybe there may be not. Then I have to extend the purple case. But here, I mean, in my opinion, very important restriction of my method is I have to start with some fixed action.
Yes.
And in this fixed action, I'm trying to change ZV1. However, if the really machine learning should be powerful, then machine learning should give you the action itself.
Yes, that's one question I want to ask. So maybe because we have in the form of the action, maybe you have find no answer.
Yes,
possible.
Yeah.
For example, here you consider linear resistivity.
Right.
We know some recent experiment from conduction matter. We say the resistivity at a strong magnetic field will scale like T square plus B square root. That's the new development.
I see. Okay.
Yeah, I think in this set of action, I think maybe cannot.
Right.
Yeah.
Right.
Using machine learning. Yeah.
Yes.
Maybe you have square root or something else.
Yes. Right. So there are many limitations in this approach, but I think it's
still power enough.
Yeah. So worthwhile to try. Okay. Thank you very much.
So last slide, we say you like physics informed network. So I see another name, the physical driven neural network.
Oh, I see.
Yeah, physical driven. Yeah, okay. Something like this.
I see.
I really like physics.
I see. Yes. Yeah, so in this area, there are many developments every week. I can see the many interesting papers. So recently, there's another scheme I mean, developing is maybe concrete of something. So it claims there is a better way to design the deep neural network. So I think that it is very interesting time to study machine learning.
It's quickly developing area.
Yes.
So
Yes.
many new ideas.
Yes.
Okay,
Okay.
good. Thank you.
Thank you very much.
线上语言方案。
线上老师有没有什么问题？行。So yes.
Any question or comment? No? Okay, maybe our next speaker.
Yeah. Okay.
Is there any question on the training video? I don't know. It was there from the beginning. Okay, maybe for the previous talk. Yeah.
Okay, then we move to our last talk of this semester. So let me